Watch this. A row of bars, all jumbled up. And in a few seconds, it sorts itself, shortest to tallest. Kind of hypnotic. But the animation is not the real story. The real story is speed. Because here is the thing nobody tells you. Sorting 1 million items with a slow algorithm takes about 1 trillion operations, that is a 1 with 12 zeros. A fast algorithm sorts that same million in about 20 million operations. Same job. The slow way is roughly 50,000 times more work. That is the gap between seconds and hours. Let me show you exactly where it comes from, visually. One quick, honest note before we dig in. Everything in this video is free, no wall, no catch. This exact visual style is the whole idea behind my book, Algorithms and Data Structures, Visually Explained. 23 algorithms, each with a clean diagram and runnable Python. $24, link below. Totally optional. The full explainer is right here. Now, let us go sort some bars. First, why do we even care about sorting? It feels almost too basic to matter. But sorting is quietly everywhere. Remember binary search, find one item in 1 million in about 20 checks. That entire trick only works on a sorted list. No sorting, no binary search. Sorting is the price of admission. And it does not stop there. Every database index that makes your queries fast is kept in sorted order. Every leaderboard, top scores, high to low, is a sort. Finding duplicates. Sort first, and identical items land right next to each other. Merge 2 datasets, show newest first, rank search results, sorting underneath, all of it. So sorting is not a toy. It is one of the most run operations in all of computing. Which means how fast you sort really matters. And not all sorts are created equal. Let us start with the simple, slow family, the ones you would invent yourself on day 1. Bubble sort, insertion sort, selection sort. They all share one shape, a loop inside a loop. Watch bubble sort. Walk along the row, compare each pair of neighbors, and if the left one is bigger, swap them. Do that all the way across, and the single biggest bar bubbles up to the far right, locked in place. Then you do it again for what is left. And again. See the problem? For every one of the n items, you walk across roughly n items. A loop, inside a loop. That is n times n squared. Double the input, and the work roughly quadruples. For a tiny list, these are totally fine. On data that is already almost sorted, insertion sort is genuinely fast. But turn them loose on 1 million items? That is 1 trillion operations. This is the quadratic trap, and it is murder at scale. We need a fundamentally better idea. Here is the better idea, and it has a name: divide and conquer. First up, merge sort. The trick is almost cheeky. Instead of sorting the whole list, split it in half. Then split each half in half. Keep splitting until every piece is a single item, and a single item is already sorted, trivially. Now the clever part, the merge. Take 2 sorted pieces and zip them together into one bigger sorted piece. Because both sides are already in order, you only ever compare the 2 front items and take the smaller one. Merge the singles into pairs, the pairs into 4s, the 4s into 8s, all the way back up. Splitting in half over and over is that log n factor, about 20 levels for 1 million items. And each level does n work to merge. N work, times log n levels. That is O of n log n, guaranteed, best case, worst case, every case. Merge sort never has a bad day. The other divide and conquer star is Quicksort, and in practice it is often the fastest of them all. Its move is different. Pick one item, call it the pivot. Now partition everything else around it. Smaller than the pivot. Goes to the left. Bigger. Goes to the right. After that one pass, the pivot is sitting in its final, correct position, everything left is smaller, everything right is bigger. Then you do the same thing to the left group, and to the right group. Recurse down, and the whole thing falls into place. On average, each partition splits the work roughly in half, so again, about log n levels of n work each. O of n log n on average. One honest catch. If you keep picking terrible pivots, say, always the smallest item, the split gets lopsided. Then Quicksort degrades all the way back to O of n squared in the worst case. Good implementations dodge this by choosing the pivot smartly. But it is why we say Quicksort is n log n on average, not guaranteed. Now let us make that gap concrete. The words n squared versus n log n do not really hit until you see the actual numbers. Take 1,000 items. An n squared sort does 1,000 times 1,000, 1,000,000 operations. An n log n sort does about 10,000. Already 100 times fewer. Now scale to 1,000,000 items, the size of a real dataset. The n squared sort does 1,000,000 times 1,000,000. That is 1 trillion operations, a 1 followed by 12 zeros. The n log n sort? About 20 million. Look at those two numbers side by side. A trillion, versus 20 million. That is a wildly different cost for the exact same task, roughly 50,000 times less work. On a real machine, that is the difference between a sort that finishes before you blink, and one that hangs for minutes. That is why n log n is the whole ballgame. Now the part that will save you a lot of pain. In real life, you almost never write any of these yourself. You call the built-in, and it is excellent. In Python, it is one word. Sorted, of your list. Done. Behind that single call is an algorithm called Timsort, a hybrid that blends mergesort with insertion sort, and it is genuinely brilliant. It is O of n log n. It is stable, meaning equal items keep their original order. And it is specifically tuned to fly through the partly ordered data you meet in the real world. Java, Python, and more all ship it. So the practical takeaway is not to go implement Quicksort yourself. It is simpler than that. Know what your built-in sort is doing under the hood. Then you know it is fast, and n log n. And the sorted order it hands you is exactly what unlocks the next fast thing, like binary search. Let us lock it in. Sorting is everywhere, search, databases, leaderboards, dedup, so its speed matters more than almost anything. The simple sorts, bubble, insertion, selection, are a loop inside a loop. That is O of n squared. Fine for tiny or nearly sorted data, brutal at scale. The fast sorts divide and conquer. Merge sort splits, then merges, O of n log n, guaranteed. Quicksort partitions around a pivot, O of n log n on average. And the numbers are the whole point. At 1,000,000 items, n squared is 1 trillion operations, n log n is about 20 million. Seconds versus hours. In practice, you call the built-in, Python sorted, powered by Timsort, and you get n log n, stable, for free. So that is sorting, and the reason the fast ones feel like a different universe from the slow ones. But did you notice something? Mergesort and Quicksort both did the same strange thing. They solved a big problem by having a function call itself on smaller pieces. Split, then split again, then split again. That idea, a function that calls itself, is called recursion, and it is the engine humming underneath both of these algorithms. That is exactly where we go next. Recursion, visualized, how a function that calls itself actually works, without melting your brain. That is your next watch. And if you want the whole picture, 23 algorithms, each with a diagram and clean, runnable Python. My book, Algorithms and Data Structures, Visually Explained, is linked below. $24, totally optional. Subscribe, and I will see you in the next one.